Today we're going to revisit the concepts of the kernel and the range of a linear map, and also revisit the notion of rank, and talk a little bit about how that relates to these sets, the kernel and the range. So we have mentioned these briefly earlier in the semester, but we haven't done a systematic discussion of them yet. So that is our objective today. So let's start with the definition. So we let L be a linear map between two vector spaces, V and W. Then the kernel of this map is a subset of V that's defined as follows. It's a set of all vectors x such that L of x is equal to 0. We sometimes use the term null space for this set. And the range of L is defined, so here it's defined as follows. It's a set of all y in the target space W such that y is the image of some point x, of some vector x. So there exists some x such that y is equal to a of x. Another way you could write this is that you could let x span over all of v, and then you look at a of x, the corresponding a of x values. So in this definition, we just claim that these are sets. These are just some definitions. They define two sets. So the kernel is in V, the source region, and the range is in W, which is the target region. And now the main claim on this first slide is that these two sets are in fact subspaces. And this is very easy to show because we showed earlier on that if you have a linear map, then the image of any... So if you have a linear map like this, there was a theorem that said that if you take a subspace of V and I look at the image of that subspace under L, then the image forms a subspace of W. And it also works backwards, that if you take a subspace of W and look at the pre-image, then the resulting set is a subspace of V. And in this case, we will observe that the kernel of L is simply the pre-image of the set 0, of the set that consists of just a 0 vector. And since this is a subspace of W and L is linear, it follows that kernel of L is a subspace. Right. By earlier theorem. You could also prove it directly. It's very easy. You don't need to call that theorem. It's super easy to prove this. You know, if say you have, so alternatively, we could do a direct proof. So for instance, to prove that the kernel is closed under addition, well, if say we have x and y in the kernel of L, this means that Lx is equal to 0 and Ly is equal to 0. And then we want to prove that x plus y is in the kernel, and well, L of x plus y by linearity is Lx plus Ly is 0 plus 0 is 0. So x plus y does indeed belong to the kernel of L. So you can prove it directly. It's super easy. But it's a little extra elegant to just invoke this theorem that we did earlier. Okay, so let's look at the range. It's exactly the same. So the range of L is simply the image under L of the entire space V. So since V is a vector space, it follows that range of L equal to LV is a vector space by the same theorem. Or you could do it directly. the point here again is that this would be very easy. So you just need to prove that it's closed under addition and under scaling by a scalar. Next, let's talk about how to find basis. So now we have two subspaces. We have the kernel of a linear map and the range of a linear map. So we'll do the special case where these maps are just matrix multiplication. So in this case, we would have V is R5, W is R4, and L of X is just AX. So that's the case that we're considering. And now we're given this matrix here, and we want to find a basis for its kernel. So we already have all the techniques for doing this. So first we compute the RAF of A. And it is, after some work, I will just write it down. So this is what it looks like. And now we want to find, so remember that X belongs to the kernel of A, means simply that AX is equal to 0. And since B is the RAF of A, this is the equivalent saying B of X is equal to 0. And now we can just directly write down all of these solutions. So let's see, so we have pivot columns are 1, 2, and 4, and we have two free variables. So if we associate each column with a variable, then we find that 3 and 5 are free because they are not associated with a pivot column. So X3 and X5 are free. And then we see that X1 plus 3x3 plus 2x5 is equal to 0. We have x2 minus x3 is equal to 0. x3, let's call that S. x4 plus x5 is 0, and x5 is t. So in other words, if we take x, then we get and now we just split these into two vectors, one that's scaling s, like that. And so now we've characterized every possible solution to the equation AX equal to 0. They take this form. So in other words, the two vectors that we derived are a spanning set for the, so let's define this as V1, and that has, or why don't we call them U and V? They are vectors. Then our answer this got a little small. Is a basis for the kernel of A. Right, so obviously they're a spanning set because every solution can be written in this form X, and they are linearly dependent because if you look at the non-pivot variables, so if you look at if a linear combination of these two guys is 0, then just look at this equation and this equation, and you see if all the xi's are 0, then it has to be the case that both s and t are 0. So they are linearly independent. So in general, so let's write down the general algorithm. So given m by n matrix A, find basis for the kernel of A. You do the following. So step 1, compute RAF. And then write down general solution. So AX equal to B is equivalent to BX equal to AX equal to 0 is equivalent to BX equal to 0. Since B is in RAF form, you can explicitly write it down. Then identify the vectors associated with each free variable. And these form the basis. So this also answers the question of what is the dimension of the null space. And if we let K denote the rank, then, as we saw, the dimension of the kernel of A, it's the number of free variables, which is equal to n minus k. So this is our answer. That is the dimension of the null space. For each free variable we get one vector in the basis. So next, let's consider the question of how to build a basis for the range of a given matrix. And this method, it's not, you'll see that it's going to be very easy to execute. It's even easier actually than the method for computing basis for the kernel, but it's not entirely obvious. So before writing down the algorithm, because it might puzzle you for just a second when you see it. So let's start with doing an example, just to demonstrate how simple the method is. So we'll start with the good news. So if we take the matrix A, and let me write it down. So here's the matrix A. It's the same one we had over here. And the solution is very similar. So step 1 is to compute the RAF of A. So here it is. There is the RAF of A. Now, the second step is to identify the pivot indices. Identify the indices of the pivots. Right, so what are the pivots? So the pivots, we have this guy, and we have this guy. So the corresponding indices are 1, 2, and 4. And now, step 3 is super simple, which is you simply pick the corresponding columns of A. So pick the corresponding columns of A. So we want to pick column 1, column 2, and column 4. So that's this vector, it is this vector, and it is this vector. Now the answer is simply the basis consists of the vectors 2, 0, 0, 1, 2, 1, minus 1, 1, and 0, 1, 0, 1. And that's it. So notice how simple this is. You start with the matrix, you compute the RAF, you know how to do that. Then you just identify which are the columns that hold the pivot elements of the RAF, and then you just extract the corresponding columns of A. So now the question that's not entirely obvious is why this works. So let's see if we can argue. I'll need a little bit of space, so let's delete the specific solution and let's address the question of, so we'll ask two questions. So why does this work? And we need to show, first of all, so question 1 is it a spanning set? And the second question is, are they linearly independent? So we will address these in order. So question 1. Is the resulting set of vectors a spanning set? And the answer is yes, so we'll motivate why. So note that y belongs to the range of A. This happens if and only if the system AX equal to Y is consistent. Because remember that A times X is, this is a linear combination of the columns of A. So x1, the first coefficient of the vector x, scales the first column, x2 scales the second one, and then you simply form, so A times X is simply the linear combination of the columns of A where the expansion coefficients are given by the entries of the vector x. So we know that y belongs to the range of A if and only if the system AX equal to Y is consistent. And now we know that, so once we reduce AX equal to Y, we get an equivalent linear system whose coefficient matrix is the RAF B. And now notice that then when you build a solution, you could simply set all the free variables to 0. So when you compute, when you've built the RAF of AY, you can build a solution X for which all free variables are 0. So you simply don't bring in any components from the third and the fifth column. So in this case, the free variables are 3 and 5. These are the free variables. So this is what we called S and T on an earlier slide. And if you just set S and T to be 0, then you get the solution vector X whose only non-zero entries are in position 1, 2, and 4. And that will precisely build you a linear combination. It will form Y as a linear combination of the corresponding of the pivot columns of A. So then AX is a linear combination of the pivot columns of A. So this is how you choose them. Alternatively, you could, so let's delete this. So another way of answering this, I'm not going to do the full details, but just to give you a hint. So alternatively, you could show, you can easily show even that any non-pivot column of A can be written as a linear combination of the pivot columns. So what you do is you seek a solution to AX equal to 0, and this is equivalent to BX equal to 0, and now things work exactly the way we built a basis for the kernel. So for each free variable, you build a solution that's 1 in the corresponding slot, and then you just get the expansion coefficients from the pivot columns. So that's a good exercise to do. I won't do the details there. So that was the first question. So the second question is, why are they linearly independent? So let's address that. So question 2. Are the resulting vectors linearly independent? And the answer here, or they are, I've claimed that they are, so we know the answer, but why is that? Maybe that would be a better way of phrasing this. Why are the resulting vectors linearly independent, or how can we know this? Well, the reason is, so if we form the matrix A prime that holds just the pivot columns. Then its REF B prime takes the form identity on top of the zero matrix. So this means that the columns of A prime are linearly independent because this matrix has no null space. No non-trivial null space, I should say. So in our specific example, we had what I mean is that A prime, so that corresponds to these three red columns. So we have 2, 0, 0, 1, 2, 1, minus 1, 1, and 0, 1, 0, 1. Then B prime is formed simply by the corresponding columns here. So that's the first column of B prime, that's the second column of B prime, and that's the third column of B prime. So B prime looks like this. Right, so if you take the RAF and you throw out all the non-pivot columns, what you end up with is something that has an identity matrix on top and then zeros underneath. So by definition, pretty much, there are no free variables in the RAF, which is to say that the columns are linearly independent, which is to say that we have successfully created a basis. So let's explore some consequences of this. So we have seen that the dimension of the null space of a matrix, so this is equal to the number of elements in the basis, and this is equal to the number of pivots, and this by definition is the rank of A. So here is a nice little theorem, which is that the dimension of the kernel of the null space is the rank of the matrix. So remember that we defined rank as the number of pivots. And we have another theorem that says something about the, so here I talked about the, no, what am I doing? This is not the kernel that I just talked about, this is the range. So the kernel is next. So the dimension of the kernel of A, well, what is this equal to? Well, if we think about the algorithm that we derived, we found that how many elements were there in the basis? Well, this was equal to the number of free variables. And this is equal to n minus k, if A is of size m by n. So I should have perhaps written that early on. So that's right, A is m by n. I should have done that to start. And k is the rank. All right, so by the algorithm we had for constructing a basis for the kernel of the matrix, we found that there was one basis element corresponding to each free variable, and the number of free variables is equal to the number of columns minus the rank. So what we get here is n minus k. So n minus rank of A. And all right, so now we have two theorems, and if we combine them, we get another theorem. So if you add these two, so this is really a super simple consequence of the previous two. So let A be an m by n matrix. Then if you add the dimension of the range to the dimension of the kernel, then you end up with n. And the proof here is very easy, of course. So if we take 1 and 2 and we add them, so by 1 and 2, the dimension of the range plus the dimension of the kernel, this is equal to k plus n minus k, which is equal to n. So, it's the third theorem here is really a immediate consequence of the first two. But the reason that this is interesting to write down is that this can actually be extended to general vector spaces, or reasonably general vector spaces. So our next theorem is really the same as this theorem, but now let's do it in the context of a general vector space. So then it looks like this. So theorem, let V and W be vector spaces, and we suppose V has finite dimension. Then we let L be a linear map, and then the claim of this theorem is that relation 3 holds. So if you take the dimension of the range of L, so L is no longer a matrix, it's a linear map. So in a general vector space setting, if you take the dimension of the range and you add the dimension of the kernel, then this is equal to the dimension of V. And the proof, we won't go through the details, but the idea is to pick a basis for V, then you form matrix associated with A, with L, and then you apply previous theorem. And the details that I'm leaving out is that, well, in order to form a matrix, you also need a basis for W, but I haven't made any assumptions about the dimensionality of W. But so the little twist here that you need to spend a little bit of effort on is that you actually don't care about all of W. You only care about the range of L. And the range of L cannot have a dimension that's larger than V, so the range of L is a subspace of W. So you pick a basis just for that subspace, and then you can build the corresponding coefficient matrix for L, and then you can apply statement 3. So the final thing we'll talk about in this lecture is talk about how does the rank of A relate to the rank of A transpose. So let A be a matrix. And it's a completely general matrix. So it can be singular, it can have full column rank, full row rank. I mean, so we already talked about many of these concepts, but remember that the way we defined rank, our rigorous definition was that it's the number of pivot elements in the RAF. So our definition of rank was that the rank of A is equal to number of pivots in the RREF of A. And this raises the question of what is the rank of a transpose? Because the way we defined it, notice that there's really no obvious connection between the rank of A and the rank of A transpose, because if I were to do row reduction on A, that really has no obvious connection to doing row reductions to A transpose. It would be sort of, you reflect it through a 45-degree angle, and then what used to be columns of A then become the rows of A transpose, and you're really operating on the columns of A. And it's sort of a priori, at first, there's no reason to believe that there's any obvious connection between these. But with the various facts that we've established, you can now see that the rank of A has to equal to the rank of A transpose, because we showed that the rank of A is also equal to the dimension of the range of A. And this is equal to the dimension of the column space. So remember, the column space is the it is the span of the columns of A. And it follows that the rank of A transpose, well, this then is the dimension of the row space of A, because the columns of A transpose are the rows of A. And remember, the row space is the span of the rows of A. But now recall our algorithms for building bases for the column space and the row space. And the point is that they both result in a basis that has exactly as many elements as there are pivots in the RAF of A. Both result in basis with a number that hold. Both result in bases that hold precisely precisely as many elements as there are pivots in the RAF of A. So now the bottom line is that so I hope you remember our method for, let's do this as a little aside, how I find basis for the row space of A. When you do RAF, so you apply row operations to A, that results in the RAF B, then the non-zero rows of B form a basis. Right, so that was the algorithm. So now that we remember that, let's write down the final result of this slide and of this lecture, which is that the rank of A is equal to the rank of A transpose. And our path to get there was slightly convoluted, but just in a nutshell, once you know that the rank of A is equal to the dimension of the column space, then it follows immediately that the rank of A transpose is the dimension of the row space. And by our algorithms for building bases for the column space and the row space, we in both cases end up with bases that have precisely as many elements as there are pivots in the RAF of A. And that was our definition of rank.